All right, welcome to video 10, and we're continuing on with vector spaces. I didn't give you the homework last time because I wasn't really sure how I was going to handle this, but now I have it. This is homework 4, due Monday the 28th, I think. Yeah, next Monday. And this is an interesting section. This is 4.2 and part of 4.3 because it's sort of a little break in the action. So if we recall linear transformations or linear transforms and the null space of a matrix and the column space of a matrix, you're kind of up to speed with what's going on in this section. So I'm going to jump to the fun stuff, and because now we're going to define a linear transformation in terms of vector spaces that aren't Rn. So we define a linear transformation from a vector space V to some vector space W, not necessarily Rn anymore. And all we say is that that should be a T for linear transformation, T. Okay. And T acts on vectors X, where X is in V, and then sends them to W. And just like before when we defined vector spaces, two rules hold. For any U in V, it must be that the sum is the vector of the sum is the sum of the vectors, so it's closed under addition. And remember, this addition might be different than what you're remembering from Rn. Usually it isn't, but and then it's closed under scalar multiplication, so T times Cu is equal to C times T of U. Okay. We define a new term, the kernel of T, which is denoted ker T, is the set. I'm gonna do this right. This is so the kernel of T are all the vectors in V that map to the zero vector. So T of U equals 0 vector, and this 0 vector is in W. So it takes, so here, let's say I had this vector space V over here. Sorry. So this is, go away. This is vector space V. So there's vectors V1, V2, the 0 vectors in there. And then over here, we've got W. And W has its 0 vector and some other vectors. And so here's another V3. So T takes V into or onto W, depending. And the set of vectors that map to 0, so let's say T of V3 was 0, then V3 is in the kernel. And let's say V2 maps to W2, so V2 is not in the kernel, right? And 0 always maps to itself, so it's definitely going to be in the kernel as well. So 0 it's always in the kernel. Okay, so we've defined the kernel of T. It's a very dear old friend of mine. And we're going to define the range of T which is just It's just T of U for U and V, right? It's just the images of all the U's under T. So to tie this together, key or note, I think it's a key here. If T happens to arise as a matrix transform, i.e. T of x equals A of x for some matrix A, then the kernel of T is just the null space of A, and the range of T is just the column space of A. Okay? So this definition is much more general, right? When we come back up here and we talk about these vector spaces, you notice this isn't Rm to Rn. This could be anything to anything, as you'll see in a minute. But for sure, we've done Rn already. That's the original example. And now we're saying, oh, there are other vector spaces to be excited about. Okay. All right. Well, this is really about me having a bit of fun with a proper example, and one of my favorite non-Rn vector spaces. Okay. So here's example one. It's actually one of the problems from the back of the book, and it's just like one of your homework problems, only I think this one's slightly harder. Okay, so we're going to define a linear transformation T that takes P2 into R2, right? And remember, P2 is the set of polynomials of at most degree equal to 2. It's one of my favorites, right? And what we're doing here is we're taking quote unquote vectors in P2 and mapping them to R2. And here's the definition. I take T and I input a polynomial. So the input to this is a polynomial. And I have to map it to R2, so I need to map it into a vector. And here's the vector. For each P, I take the P and evaluate it at 0. Okay? So this is the transformation. Or transform. I used to go back and forth between those two words. Okay, so now this is really fun. Now, so 1, we want to find polynomials P1 and P2 that span the kernel of T. And then 2, we want to describe the range of T. All right, so let's just take a little sidebar here for a second. So example within the example. We'll call it example 1 dash. Okay. Note that the polynomial P sub T equaling T plus 1 is in P2, right? Polynomial Q of T, T squared plus 2T minus 1, that guy's also in there, just to muck around. And let's see here, and these are actually, I know it's weird, but these are vectors. And let's go 3t cubed plus 6. This is not in P2 because it's a third degree polynomial. Okay. All right, so for all of these, just because we're looking at this transform, P of 0 is 1. Q of 0 is minus 1. And R of 0 is 6. So basically what this, well here, let's compute T of P, this P here, the one we're actually going at. I get the vector 1, 1. Right? Because P of 0 is 1, and I have P of 0 and P of 0 as my definition right here. Okay. All right, so let's see here. Okay, now we're going to answer part 1. The kernel of T are the polynomials in P2 such that P sub 0 equals what? 0, 0, right? So it's mapping all these vectors over here to the 0 vector in R2, right? Okay. So this says that, so P, it must be that P, which has the form AT squared plus BT plus C, that's a second degree polynomial. It must be what? That C equals 0, right? That must be the case here because we're going to map to the 0 vector each time, and the constants need to be, these constants need to be 0. Okay, so P is the set of all polynomials that look like this. AT squared plus BT in P2, right? Okay. And so this is what the kernel of T looks like. It's going to have all the vectors with 0 constant coefficients as the third term. Okay, so remember, now we're looking for this. Now we're looking for two vectors to span these guys. And this actually took me a minute. I thought about it and I was like, wait, what am I missing? Well, remember what the span is. The span is the linear combination of vectors, all linear combinations of vectors. So P1 is that, and P2 is this, right? Because if you take any linear combination, so A P1 plus B P2, what do you get? You get AT squared plus BT. Okay? So these two vectors are the span of T, so a span of the kernel of T. So the kernel of T turns out to be the span of the two vectors T and T squared. Okay. That was so cool. All right, I hope you guys enjoyed that as much as I did. Part 2, describe the range. Describe the range of T. All right, so now we're not talking about the kernel anymore. We're talking about the entire transform. So let's do another example 1 double dash, just to have a moment here. Let's pick some random vector. I'll call it P3. In P2, I'm going to say it's 2t squared plus 3t plus 1. And what's t of this guy? It's the vector 1, 1. Okay. Let's pick another P4 minus 3t squared minus 6. And what's the image of that? Minus 6, minus 6. And again, this is a vector in R2. So is this, right? Because the mapping goes from P2 to R2. P2 to R2. And there actually is a D2, so pretty soon we'll be talking about transforms from R2 to D2. But that's for later on. Okay, so all these vectors lie on the line x1 equals x2, right? Because if you're now in R2, which we are, there's the vector 1, 1. There's the vector minus 6, 6. So it's always just going to be the constant times itself. So the range of t is the line x1 equals x2. All right, well, that was pretty exciting. I gave you a problem just like this, but a little different. It's actually, I think, a little easier because he talks you through it. And it's also an odd, so you can actually look at your solutions. But just note that the P's, well, and the D's, and the M2s. All right, anyways, this is my favorite. So I'm going to try and, it's my favorite vector space, if it's possible to have one. And you'll see a lot of examples this term with these. All right, talk to you in a bit.